All right, in this video, I'm going to go through and just do a bunch of example problems with condensing, combining, expanding, evaluating, all that fun stuff with logarithms. So following the instructions, condense each expression to a single logarithm. So when you're condensing, the first part you always start off with is this constant multiple that's out front because you want to technically, this means that there are 3 logs here, and so we want to combine those logarithms into one by taking our constant multiples and putting them inside of your logarithms as exponents. So we can rewrite this as log base 9 of 2 to the 3rd power minus log base 9 of 5 squared. And we'll actually go ahead and we'll simplify at the end the 2 to the 3rd and the 5 squared. But first, I see one more way that I can combine these two logarithms. If I have subtraction outside of logarithms, that turns into division inside of one logarithm. So I'll have log base 9 of my first term, 2 to the 3rd, divided by my second term, 5 squared. And then when we simplify that, we get log base 9 of 8 over 25. We're not evaluating the logarithm, so I'm not expecting you to now plug this into your calculator. We're just practicing condensing them in this set of examples. All right, with these logarithms, I again look for if I have any constant multiples out front, and I do, so that comes up and becomes an exponent inside of your logarithm. So then I'll have log base 6 of x plus log base 6 of y plus log base 6 of z to the 6th power. And then what I notice is between all of these logarithms, I have addition happening. And so anytime I have addition happening outside of logarithms, I know that I can combine them all into one logarithm. Or if you want to do it like one step at a time, you could do that as well. So we could do that. These two logarithms, addition between them, would combine into one logarithm, base 6 of x times y. And then we still have this part bring down. And so more obvious of what I was doing there. So I combined those logarithms, and now I still have addition between these two logarithms. So now I can combine those, and I can still do multiplication. So xy times z to the 6th. So I'll have xy z to the 6th is my final answer. And now I'm done because I know I'm in a single logarithm. There's nothing else I can like simplify. Like there's no regular numbers or anything like that. All right, let's look at this example. So I have some constant multiples out front, so I'm going to bring those inside of my logarithms as exponents. So I'll have log base 5 of x squared plus log base 5 of y to the 12th power. And then I notice that I have addition outside or between two logarithms, so I can combine those into one logarithm with multiplication on the inside, log base 5 of x squared times y to the 12th. There we go. All right, let's do some more of these examples. So these ones are a natural log, but that's okay. It's still a logarithm. So first thing I look for is constant multiples out front, because I know I can bring those up to become exponents. On this one, be careful because all of this stuff is what's inside of the logarithm, so the exponent will go on all of that stuff. And you'll see what I mean in the next step. So natural log of 5, nothing changed about that, plus natural log of now an x squared plus natural log of x squared plus 5 to the 3rd power. So that third is applying to that whole, that entire parentheses there. And then I see addition between these two logarithms. So I can have natural log of 5 times x squared, right? Addition outside turns into multiplication inside. And then nothing changed for this part, so I'm just going to bring it down. So plus natural log of that stuff. And then I notice between now these two logarithms, I have addition, so it turns into multiplication inside of one logarithm. So this one, watch out, you're going to have multiple sets of parentheses because we'll have 5x squared times the x squared plus 5 cubed. So I basically, because I took this piece and I'm multiplying it by this piece, but now just inside of one logarithm. And we're done. Remember, there's no addition and subtraction. You can't simplify that anymore inside of your logarithm. So, all right, let's go ahead and look at this one. So first and foremost, I do notice that I have a constant multiple 2 up front of all of these. So I'm actually going to go ahead and distribute it first like a normal number. So it's going to be 2 log base 5 of x plus 2 times 2 is 4 log base 5 of y minus 2 times 3 is 6 log base 5 of z. Okay, and so then now, looks like a normal problem to start off with. I'm going to go ahead and that was regular distribution. I was just multiplying everything by 2, and now I'm using the rule, the fact that if I have a constant multiple up front of each logarithm or any of the logarithms, I can move it inside of my logarithm as an exponent. So I'll have log base 5 of x squared plus log base 5 of y to the 4th minus log base 5 of z to the 6th. I notice with these two logarithms, I have addition between them, so that's going to actually turn into multiplication inside of one logarithm. So log of x squared times y to the 4th. And then I still have nothing changed about this piece. So I'll have minus log base 5 of z to the 6th. Oops, 5 over here. All right, and then for my last step for this one, I have subtraction between these two logarithms. So subtraction outside of logarithms turns into division instead of one logarithm. So I have log base 5 of my first stuff on top, so my x squared y to the 4th, over being divided by the second piece, my z to the 6th. And now that's done because I have one logarithm, and I can't do anything else in there. All right, let's do these next three. So I'm going to go ahead and I see some constant multiples, so I'm going to put those up as exponents inside of my logarithm. So this will turn into log base 2 of 3 cubed minus log base 2 of 7 to the 12th power. And then subtraction between two separate logarithms turns into division inside of one logarithm. So 3 cubed over 7 to the 12th. My goodness, that's going to be a big number. Log base 2, well, 3 cubed is 27. 7 to the 12th, I got to do in my calculator. Hold on one second. 7 to the 12th power. Holy crap, we're just going to leave that as 7 to the 12th. My goodness. Even in my graphing calculator, it gave me scientific notation, so that sounds good right there. All right. Let's go ahead and do this next one. So on this one's a little tricky. We're going to rewrite it first. So let's just put it in a different color. So we have 2 log of 5z. Another way to write this is if I have log base 5 of x and then the whole log is being divided by 2. Another way I can write that is it's 1/2 times that logarithm, log base 5 of x. So now it looks like something that's in a form that we can actually work with. It's a constant multiple out front, so I'm going to go ahead and bring those to be exponents. So I'll have log base 5 of z squared plus log base 5 of x to the 1/2 power. And then addition between these two logarithms, outside of logarithms, turns into multiplication inside of one logarithm. So z squared, oops. And then x to the 1/2, except for we are advanced mathematicians and we never leave our answers with fractional exponents. So what you can actually do is laws of exponents say that if you have, write it off to the side somewhere, if you have an x to some power, some fraction, that's your power over index, that means that we can rewrite that as the index root of x to that power. So if I have, for this example, I have x to the 1/2 power. So I'm going to do the square root, because that's my index, the square root of x. So I still have that z squared, that was still there. And then instead of writing x to the 1/2, it's the square root of x to the 1st power. So that's your final answer for that one. So it's kind of nice because we're practicing our exponential expression stuff as well, at least with fractional exponents. All right, for this one, this example, we're going to do the same thing here that we did with this logarithm. These natural logs, we're going to rewrite them in a way that puts that division by 3 as a constant multiple up front, so it's really 1/3 natural log of x plus 1/3 natural log of y. And then now I notice this doesn't have any constant multiples, but this one does. Whoops. So I'll have natural log of z plus natural log of x to the 1/3 power plus natural log of y to the 1/3 power. And then I have addition. We're at the last example with combining, right? Regular condensation. So we're just going to add all these. So we're actually just going to combine them into one logarithm that has everything multiplied. So z times x to the 1/3 times y to the 1/3. And then again, because we won't leave our answers as fractional exponents, we're going to rewrite it using a radical. Same power over index rule applies, so my index here would be 3 and my power is 1, so really I'm just looking at the cube root. And you can write it in 2 different ways, and I'll show you the 2 different ways. So z, and then you can do cube root of x, cube root of y, or if you want to get extra fancy, you can go ahead and, since those are both underneath the cube root, you can just kind of put them both underneath the same cube root. Crazy, I know. Not the z. The z is just over here. He doesn't have an exponent. He's just hanging, but the x and the y. Cool. All right, so that's where I'm going to pause this first set of example videos, and then I'll go ahead and do some more.